So this video is an introduction to power series. We've actually already seen power series in the last few videos. For example, we have the identity that 1 over x is equal to this infinite sum from j equals 0 to infinity of x to the j, at least for all x between -1 and 1. And so more generally, power series are identities that look like this. We have some function here, f of x, and on the other side we have something that looks like an infinite sum of polynomials. And so the sort of general question that we ask when we're talking about power series is the following. For which functions f from some domain a to r, and for which domains a, can we find coefficients, real numbers aj, so that we have this identity, f of x is equal to the infinite sum from j equals 0 to infinity of aj times x to the j. We're going to start answering this question in this video and then continue in the following video. But before doing that, I think it's important to ask the question, which is, why would anybody bother to try doing this? There are a lot of answers to that question, and some of them are, well, most of them are far beyond the scope of this course, but at least I'm going to give it a shot so that we have some idea as to why we're interested in this at all. And I think the easiest answers come from the following two related ideas. The first of this is that as we start studying convergence properties of power series, we learn how to find new power series. So that is, if we can find a few power series, we can use those and we can use formulas involving the power series to find new ones. So we can sort of expand our vocabulary of power series. We've actually seen this already when talking about formal differentiation, that is, swapping the sum and the derivative symbols. So if you look at the last video, we saw that 1 over 1 minus x squared was equal to the sum from j equals 0 to infinity of j times x to the j over the same interval x from -1 to 1. And we found this formula by taking our earlier formula up here, hitting both sides with a derivative, and then justifying this idea of switching the derivative and the sum symbol. So that's not 100% obvious that you can do that. We proved you could do it for that particular case, and one thing that we're going to do by developing a general theory of power series is come up with more ways to do that sort of trick, and thus come up with more and more power series. All right, that still feels like a little bit like it's begging the question. We get more of these formulas, but what do we actually use them for? Well, there are a few different things, but one really nice reason to use power series is that they let us do a sort of formal guess and check approach to solving lots of equations. That's actually sort of where this subject got started. And I'm not going to try to sort of give any sort of generic theory about how this type of guess and check gets worked. But one thing that's nice is you can just sort of try it. So here's one example of something you might try. This differential equation here is called the area equation. And so the question we try to answer when we're trying to solve something like the area equation is, give me a function f that satisfies this equation. Now, if you stare at that, it seems not so obvious where such a function f should come from. Certainly, I don't know any really easy tricks for doing that. And the power series guess and check approach is the following. We're going to guess that f has this formula here for some sequence aj. And then what are we going to do? We're going to take formal derivatives. That is, we're just going to pretend that this sum here is a finite sum and differentiate all over the place. Now, when we're doing this, we might be hitting something wrong, right? It's not 100% clear yet that this sort of formal differentiation is actually going to work. We can try it anyways. We can guess and then we can check. And if you do that, this equation here becomes this equation here. We're just taking derivatives of a bunch of polynomials. And if you look at this and you match the terms which have the same degree here, that's going to tell you that aj satisfies the recursion aj is equal to aj minus 3 over j times j minus 1. Now I say this is equivalent. We really haven't justified that yet, but you can sort of guess that that should be true. That is, that the coefficients for matching terms had better be equal. And that's sort of nice because we can solve this recurrence. We can set a0 equal to some constant a. And we can set a3 using this recurrence to be a over 3 times 2. a6 is equal to a3 over 6 times 5. That is a over 6 times 5 times 3 times 2, and so on and so forth. And so we end up with the following power series representation for f. It's equal to a times, and then this big sum over here. So that's sort of cool. Just to recap what we did, we started with the differential equation. I have no idea what solutions to that differential equation look like, but we guess that it looks sort of like this. We just sort of start taking derivatives without really worrying about whether we're justified or not. we end up with this cool recursion here, and it turns out we can solve the recursion, and so we get really a formula for f of x. Okay, that's not very obvious that you could do that, and there's some real power in doing so. And that again sort of feeds back into the first reason. As we learn more about power series, we're going to learn more and more properties of them, and so we're going to be able to better and better identify what these guesses really mean, which right now is maybe not 100% clear. So all of that was quite informal, but that sort of justifies why we bother doing any of this type of work, and indeed it turns out that this sort of approach really does work for a fair number of real problems. Okay, that was story time. Now it's time to go back to math. And let's talk about a couple of explicit sequences of power series. So here we have 3 power series that I've written up here, and I'm going to talk a little bit about where they converge and where they fail to converge. So this one here in the middle is the one that we've seen already, and we saw in last video that it converged on -1 to 1, and we saw that it diverged on, well, -1 to 1 complement. Okay, so that one we already saw, and actually that's probably the most delicate argument. This first series here, we take the same series except we multiply all of the terms by this enormous number j to the j. And certainly this converges on the set, which is 0, right? If x is 0, then you're just summing 0 many, many times. And it turns out it actually fails to converge everywhere else. To see why that's true, imagine that we have some number x with absolute value x greater than 0. Well, then the absolute value of j of xj to the j is going to be bigger than, say, 2 to the j for all j bigger than some big J sufficiently large. And of course, we certainly know that if you try to sum 2 to the j, you're going to run into problems, right? So there's no way that that can possibly work. That's a bit of an informal proof, but it's not so bad to turn that into something a little bit more careful. This third series, we now take the same thing, except instead of multiplying by a huge number, we now divide by an enormous number. And it turns out that it actually converges absolutely everywhere, and basically by the same argument that we just did, as long as we have some x that's finite, then x over j to the j is less than 2 to the minus j for all j sufficiently large. And so by, for example, the Weierstrass M test, we can see that this thing is going to converge, and in fact converge uniformly on compact sets. And of course, since we've shown that it converges everywhere, it fails on the empty set. Okay, so those are 3 sort of power series, and a sort of quick informal argument as to where they converge and where they fail. Now, it's a little bit hard to just do these arguments for every individual power series, so we want to develop a little bit of a theory. And for the rest of this video, I'm going to have the following notation. I'm going to let sum k equals 0 to infinity of ak x minus c to the k be some power series. And now we're going to give a little bit of notation. We define the radius of convergence of that power series to be the 1 over the lim sup as k goes to infinity of ak times 1 to the k. Now, let's just think for a second off to the side before we do some mathematics. What does that radius really mean? Well, what it's telling us is that for all k fairly large, ak is less than 1 over r, right? And so what does that really mean? Well, let's imagine that ak was actually literally 1 over r for all k. We would end up with the power series sum, to the k of r to the minus k x to the k, and just looking at this, you can see that this is going to converge as long as x is less than r, and it's going to diverge when x is bigger than r. So this is sort of the heuristic, right? When we're looking at this lim sup, we can imagine what happens if we actually have equality for all k, and we end up with this sequence here, where it's fairly easy sort of by inspection to see where convergence is going to happen and where convergence is going to fail. And it turns out actually that heuristic is going to be extremely accurate. So we have the following theorem. If r is equal to 0, then this sequence converges at x equals c only, and it diverges everywhere else. If r is equal to infinity, then the sequence converges absolutely at every point. And if 0 is strictly less than r, which is strictly less than infinity, this converges absolutely on the interval c minus r to c plus r, the open interval, and it diverges on the complement of the closed interval from c minus r to c plus r. Now, of course, I haven't said what happens at C plus R exactly and C minus R exactly, and it turns out actually there's a bit of subtlety there, so this theorem doesn't tell you exactly when convergence happens, but all right, except possibly for 2 points, it tells us what's going on. How do we prove something like this? Actually, the proof is essentially just the root test. Proposition 3.19. There's almost nothing else to do once you've looked at that theorem again. Okay, so that's convergence. What about better properties? Well, it turns out that actually in the same situation, you get uniform convergence on any compact interval that's contained inside C minus R and C plus R. Okay. So in other words, we have convergence on C minus R, C plus R, this open interval, and uniform convergence on any smaller interval that's contained inside of that open interval. How do we prove something like this? Well, we're going to be going again basically back to this intuition where we could just use the Weierstrass M-test, but we have to be a little bit careful, so let's be careful. I define script L to be the maximum of A minus C and B minus C in absolute value. And remember from our assumption, right, the interval from A to B is a subinterval of the interval from C minus R to C plus R, and so L is strictly less than R. I want to be using the Weierstrass M-test, so I define Mj to be L times Aj. And of course, we're going to check that this Mj works more or less for the Weierstrass M-test. Now I let epsilon be 1/4 times R minus L. Now, since epsilon is less than the difference between R and the maximum of A minus C and B minus C, what we know is that actually for all j sufficiently large, the absolute value of aj is less than 1 over r minus epsilon to the j, right? This is more or less just from the definition of the lim sup. In particular, for all j less than the same k and all x in this interval from a to b, mj is less than r minus 4 epsilon over r minus epsilon to the j. I can rewrite that as 1 minus 3 epsilon over r minus epsilon. So this thing is strictly greater than 0, which means this thing is strictly less than 1. And so if I want to be looking at the sum of the mj's, I find that the sum of the mj's is less than sum j equals 0 to k of epsilon mj plus sum j equals 0 to infinity of this thing here. I'm adding up powers of something that's strictly less than 1, so in fact that sum converges, and I end up with some initial terms here, plus a constant r minus epsilon over 3 epsilon, which is certainly finite. So what have I done? I've checked that these terms here in fact converge. And I've checked that at least for all j sufficiently large, larger than some fixed constant k, these mj's are in fact an upper bound on the individual terms here of the sequence. And so applying the Weierstrass M-test, I've checked that in fact we get uniform convergence of the power series to the function f. All right, that's it for sort of the introductory material. We've seen what power series are, and we've seen what the radius of convergence are, and we've seen how convergence worked within the radius of convergence. In the next few videos, we're going to talk about some further properties of the power series. Thanks.